Igneous Rocks, Part 4, Magma Movement and Intrusions. Here we have a blob of magma that is moving up through what's known as the country rock. Now, country rock is the rock that was there before it was intruded upon by magma. Country rock is often sedimentary, and you can tell sedimentary rock because sedimentary rock typically has layers to it. So here's the magma moving upward. If it makes it all the way to the surface, what do you have? Kaboom, you've got a volcano. But very often the magma cools before it can make it all the way to the surface. So if it cools on its way, turns into a rock, you have what's known as a pluton. A pluton is igneous rock that cooled deep underground in the realm of Pluto. Why does the magma rise? Well, it does so for the same reason many things rise. It is less dense than the rock around it. There is, of course, a much more scientific word for blob of magma. It is called a magma diapir. You have seen a diapir if you've ever seen a lava lamp. This blob about to go upward, that's a diapir. Remember that these blobs of magma are the result of melting, often at a subduction zone. As they come up, they can interact with each other. Sometimes two diapirs can mix together, mixing their magmas. Sometimes the diapir of magma can interact with the country rock. It can assimilate, take in pieces of the country rock, melting it. That will change the kind of magma. Or it can ooze its way up into the country rock, making dikes and sills. Inside the magma, crystals that are forming as the magma cools can settle down. In A, we have magma going through cracks in the rock, in the country rock, sliding through layers. As it cools between layers of the country rock, it will eventually become what's known as a sill. As it cools, as it goes through cracks in the rock, it might become a dike. As it rises, sometimes it even pushes the rock above it into what's known as an anticline, a curved layer of rock. Or sometimes it just eats up the rock it's coming through. The chunks of the rock can be totally assimilated and melted, or they can be partly assimilated and be left behind as foreign rocks called xenoliths. Here are two examples of xenoliths. I'm sure you heard the word xenophobe, someone who's afraid of strangers, and lith, of course, means rock. So xenolith is a foreign rock. So here's an igneous rock, probably of a basaltic type of origin, and it's surrounded this rock here. This rock might have started to melt. You can see a chill zone around the edges where it was affected by the heat, but the center is pretty much intact. So this circular rock is a xenolith inside of the igneous intrusion. So is this. The darker rock in this case was there first, and the lighter rock, the lighter igneous rock, surrounded it and became a xenolith. As I said, the layers of magma that come across the existing layers of sedimentary rock are called a dike, D-Y-K-E, or in the United States we usually spell it D-I-K-E. It will also have an effect by heating up the rock on either side, sometimes even turning it into metamorphic rock. And here's the sill, the magma that intruded between the layers of the original sedimentary rock. Years later, that igneous dike that intruded upon the rock might end up being harder than the surrounding sedimentary rock, and it's left behind as this wall of rock. Here we have a summary of many different kinds of igneous intrusions. You start with magma, and the magma will cool to become a batholith. A batholith is a very, very large intrusion of magma that has cooled deep underground. The whole Sierra Nevadas are a big batholith. They're made of granite. And if you look at the highest place in California, Mount Whitney, you stand on the top of Mount Whitney, you are standing on rock that started miles underground and has since been lifted up. Well, if that magma comes to the surface, we have a volcano, and this volcano here is most certainly a composite volcano. How do you know? Well, you've got ash coming out of it now, you've got a nice cone shape, and here we have a lava flow. As the lava flow cools, there we have a layer of basalt or andesite or rhyolite on the surface. If, however, the magma never got to the surface, it could have formed a sill or a dike. Or, here we have another dike and another sill. If the sill, however, pushed the rock up above it, you can have this kind of mushroom-shaped intrusion called a laccolith. And here's a laccolith that is now pushed up to the surface, and the once curved layers of sedimentary rock that were around it are eroded away. This here would be what's left after the volcano has eroded away. It's called a volcanic neck. Here we have a layer of igneous rock that formed deep underground. It's in the form of this. This is a beautiful intrusive feature. It's called ship rock because at a distance it looks like a big sailing ship sailing across the desert. This rock, which is huge, these are roads, is what's left of a volcano after the rest of the volcano has long since eroded away. The center of that volcano was hard magma turned into hard rock, and radiating out of that volcano there were dikes, and those dikes can still be seen coming out of shiprock. Here's another picture at a greater distance. You can see the volcanic neck and the dikes radiating out. The beautiful rock that sits in the center of Morro Bay is an old volcanic neck. The largest intrusions of all are called batholiths. No, I'm not lisping. It really is a batho, which means deep, and lith, which means rock. All of the granite of the Sierra Nevadas, including Yosemite National Park, formed deep underground over a subduction zone back in the Jurassic. All of the volcanoes from that subduction zone, long since gone, but the granite has been lifted upward, and we see them exposed here in Yosemite National Park. So how did this form? You're looking at a rock layer. There's a rock hammer to give it scale. What formed first, this darker rock or the lighter rock? Well, the clue is that you can see sort of flow lines here, and this lighter rock is igneous, while the darker rock is not. So the darker rock was there first, and the lighter rock flowed around it, turned into an igneous rock, leaving the dark rock behind as a xenolith. What's that? That is a volcanic neck. How about this? This rock right here looks like granite to me, but what about this oval blob? The granite surrounded the blob, and the blob, instead of getting totally assimilated and melted, just is left behind once again as a xenolith. So the blob came first. Here we have light layers cutting across a darker rock. Those light layers are dikes, and that light rock was once very felsic magma. Here we have sedimentary rocks of the Grand Canyon. But among those sedimentary rocks, there is a layer of basalt. Now, if you could find vesicles at the top of the basalt, you could say, oh, easy, that's just a lava flow. But if instead you find that this layer of basalt heated the rock above and below it, it might not be a lava flow at all. It might instead be a sill. How about this layer? This also is igneous rock, where the layers on either side of it are layered sedimentary rock. That would be a dike. And of course, the largest cliff of one single kind of rock is El Capitan in Yosemite National Park. That rock is granite, and El Capitan is part of the Sierra Nevada batholith.